Hello.
Hello. That's about just after I started sharing my screen. So I started recording, sorry. Right. We are going to look at modules and imports and namespaces. This is a core Python topic. Absolutely everything that you do with Python uses imports. It's also the nice thing about Python and the way modules behave is that they are just objects, and a lot of their behavior comes out of objects, and a lot of the behavior of Python comes out of that as well. So we have a nice consistent framework for understanding them. We can understand all of the syntax, all of the options, and also what's going on behind the scenes. It's all easy enough to understand. The talk materials, the slides I'm using and the example code are in the usual place in the github.com/voidspace/talks repository, and I shared them earlier. Right. So the topics we're going to look at, the variations of the import syntax, the difference between them and what they do, modules as namespaces and how that creates our variable lookup semantics for global variables. We're going to look at sys.modules and the import cache. That's the internal machinery for imports. And we're going to look a little bit as modules as dynamic objects with some module level functionality, which will probably be new to most people here. It's not something I've used a great deal, but it's kind of funky. We'll look at packages and their relation to the file system. Packages introduce relative import syntax, which is another import syntax variation. We'll look at module reloading, why not to do it, but how to do it when you want to. Avoiding and fixing circular imports, which are a common problem when you're working with complex Python code. And a little bit at the end, executable modules and packages. And this last bullet point is a lie. I do use dunder import once, and I mention import lib, but we're not going to look at them in detail, but it's great to know they exist. Okay, so every Python source file is a module, and all code is executed inside a module. Even when you just execute a script at the top level, that's executed inside a module. Every Python source file is a module, and all Python code is executed inside a module. So here's an example Python file, foo.py, and it contains two simple function definitions. Some other code does import foo. That import statement finds, loads, and executes the module, executes the code in the module. So import triggers code execution. We're going to skip over finding the module here and come back to that later. Once we've done the import, the name foo is bound to a module object, and everything exposed in the top level, the global namespace, is exposed as an attribute on that module object. So this is the dot operator, the attribute lookup operator. Names in the global namespace of a module become attributes on the module object. What is a module? A module is a namespace. It's a collection of named values. So the global variables here, if we go back to our module foo.py here, our module foo, you can see there the straightforward relationship between the module name in code and the source file. Every function definition is also an assignment. It creates a global variable if it's defined at the top level. If you define a function inside a function, the function object is created, and then you get a local variable where the name points to the function object. So when you do the import, Python finds this code, finds this source file, it executes it, and this creates these function objects and also binds the name. After the def statement has been executed, the name grok is bound to, refers to, points to. The name grok points to the function object. And then there's the span definition is executed. This creates the function body, and the name span is bound as a global variable in that namespace to that function object. Once that has happened, inside this module, we have the name foo, which is bound to the module object, and the objects in the global namespace of that module object, are accessible as attributes on the module object. I hope that's straightforward. So the module forms a namespace. Inside the module, global variable lookups happen inside that module, inside that namespace. From outside the module, we can access, the module is a namespace mapping attribute names to everything that lives inside the module. And so the nice thing is if you have two separate modules, here we've got foo and bar, they can both define names X. In foo, X is 42 and bar, X is 37. And looking at them from inside their module worlds, they're both both foo and bar have a name X, a global name X, but they live or are defined in different namespaces. One is foo.x, the other is bar.x. So there is no overall global scope, no overall global namespace. Everything lives, all names live in a specific namespace. And this is one of the things that's great about Python. Those namespaces, the module forms an enclosing environment. So every module is separate and distinct, and you can't clash with other modules' names unless you deliberately try to. Modules are objects, and for those of you who went to the core object module knowledge share, will know that normal Python objects have a dunder_dict, _dict, _attribute, in which object attributes are kept. Modules also have a dunder_dict, and that's where the global variables live. So you can see here the name grok, the global variable grok in foo is a reference to the function grok. So that's where the objects live. They're kept alive because there are references to them in the module dictionary. If you do have any questions at any point, or comments, or I say something that's wrong, feel free to ask. Inside every module, there are several magic variables automatically defined for you by Python. Dunderfile, dundername, and dunderdoc. Dunderdoc is the module docstring. It's created when the module is read in. Dunderfile and dundername are put into the module prior to the execution of the code. So code within a module is able to access its source file and knows its name. This means we can use the name, dundername, and you will have seen this pattern before. We can use it to tell whether our code is being run as a script or is being imported as a library. This is useful because where we use this, most languages have a concept of a main function or even a main class. This is what it looks like in C, C++. This is what it looks like in Java. And this is the code that is executed at startup time, the entry point. Python has no main function or method, but it does have a main module. So here with this invocation at the command line, Python prog.py. Prog.py is the main script. It's the main program that's being run, and that is executed inside a module, and that's the main module. So inside that module, the module that's created where this code is executed, dundername is set to dundrmain. So it's common to see in your code, particularly in your scripts, this little stanza, if dundername equals dundrmain, this means we are being run as the main script. So I can show you this really simply. I'm sure you believe me. Here we have foo.py, and all foo.py contains is the code print dundername. If I run that as the main script, it prints dundrmain, sorry. If I open up a Python interpreter and I do import foo, the interactive interpreter is always able to import from the current directory, which is useful. If we import the module, import it as a library, dundername is foo. Live coding, don't do it. So if you have code that provides some module-like facilities functions that may need to be used elsewhere, but also provides scripting functionality. It protects the entry point with this stanza, and then if the library is imported, so that in our case dunder name would be foo, this code doesn't run. It's also a useful way to structure your code by default to make your scripts more flexible. They can become libraries straightforwardly. Okay, so what we've looked at of imports so far looks a little bit like this, and you can actually find functions like this, although much more complete and supporting things like import hooks, etc., inside the import lib module, which is a pure Python implementation of the Python import system written by Brett Cannon. So our import module function, we have an import name. The first thing it does is find the module. We're glossing over that. So this gives us the file name that corresponds to the import name. We read that in as a text file. There are optionally where the default encoding is UTF-8 for your source code. And there's really no reason to use anything else for most of us. We read the code in. There are ways of specifying. So again, this code is much simplified. You can provide encoding cookies. We then create an empty module with the name. Actually, we set things like mod.dunder name, mod.dunder file on this object as well. And then we execute the source code from the source file inside the module dictionary. And this is using exec. So that's a proxy that populates the module object, and we return it. So this is a simplified version of what import does. And you can use this for dynamic module creation if you want it. The types standard library module is really interesting, and it's fun to look at the source code and see how things like module type are defined. Okay, so the import statement finds and executes the entire module. That's important. The source file code is found. It's executed inside an empty module object that just has dunder name, dunder file set, and the module object is created. So we have bar.py that does import foo. This is the same for foo module that we've been working with. And after the execution of this statement, inside foo is now a global variable. It's in the bar namespace. So if we looked in the bar.dunderdict, the underlying dictionary for bar, that global namespace, we would see the name foo referring to that module object. That name is then available in the bar namespace, so we can do stuff like calling functions defined in foo. And that's one common variation of the import statement syntax. The other variations, the behavior under the hood, is not very different. What's different is the names you end up with in your namespace afterwards. This bit about finding and executing the code remains the same, irrespective of how you import the module. And importantly, modules are only loaded once. You only need one module object in the running system. That allows you to do module level configuration, which can be shared by several users of the module, and obviously saves memory. Modules can be used in many places in your code. And you want, if you have a class defined in a module somewhere, everywhere that's using that class, you want them to have the same class object. You don't want multiple different versions of class objects from multiple different versions of the library in your system at the same time. So modules are that dance of finding the source file, executing the code to create the module, and returning the module objects. That's only done the first time a module is imported. An extra step. Once the module has been created, it's put into sys.modules, which is an ordinary dictionary. So you can perform dictionary operations on it if you want. It's not private, it's exposed in sys.modules. People do sys.modules trickery, but you have to be careful and know what you're doing. One thing you can do, every namespace has a dunder name giving you the name of the module. or the name of the namespace. And that is the key under which that namespace is stored in sys.modules. So sys.modules keeps alive all of the modules that have been imported. This is where most of the state of your running system lives. So any module can find itself in sys.modules using its dunder name. You can even find yourself and replace yourself in sys.modules with another object. I can do crazy things like sys.modules. We'll create a spam module equals object. Let's do colon equals, so it returns it and shows us the ID. I can't do that. Damn it. Okay, but if I now do import spam, it gives me back that object. So any namespace can always get a reference to itself with this code, and we can see that the underlying dictionary of the current namespace is the same thing as the globals dictionary of the current namespace. They are the same object. Globals returns you the namespace for the current namespace as a dictionary object. And this is what it is, where it lives. So a namespace is a dictionary, a module is an abstraction over the top of a dictionary, a mapping of names to objects. So we can update our pseudocode for import. Our import function is given a name. The first thing it does is check, have I already imported this? Is it in sys.modules? If I have, I can just return it. There's nothing more to do. The problem is, if you're actively developing this module and you make some changes and then you re-import it, you'll find that your second import gets the earlier version, which is already cached. This can be a pain when you're developing, which is why we get tempted to turn to module reloading, and it does work under certain circumstances, and developing code is the use case for it. Never use it in production. We'll come to that soon. Okay, so import module by name. If it's already been imported, we can just return it. What we do, and this is important, and it's important for understanding circular imports. We'll get to that a little bit later as well. The empty module is created. It's immediately put into sys.modules. This is because circular imports are allowed and can work, as long as you do them right, but they can also fail. But if circular imports weren't allowed and this wasn't how it worked, we create the module object, we start it, but we don't put it in sys.modules. We start executing the code. This imports the dependency, which starts executing that code as well. That dependency maybe imports something else, which then imports us again. So we start creating a new module, which imports the dependency, creating another new module, which imports the other dependency, which imports us again, and we've immediately got recursion that continues until we run out of memory. So before code execution, the empty module object is put in sys.modules. We'll look at that. We'll look at the consequences of that in a very practical way when we look at circular imports. It might sound frightening, only because it is, really. Okay, see the import lib module for more details. Right, the import lib module has now been mentioned. Okay. Next variation of import syntax, from module import something, from foo import grok, very common. Second form of import syntax. Useful for frequently used names, useful for unambiguous names. If the grok function, everyone knows that comes from foo, you don't need foo.grok. And there is a cost. That's the dot operator, the attribute lookup operator. It goes through the attribute lookup protocol, and we'll see how that's useful shortly. The import behind the scenes follows exactly the same pattern that I've just described. The source code module is located and read. An empty module is created, put in sys.modules, and then the source code is executed inside that module dictionary, inside that module global namespace. The difference is that after the import, we don't have a direct reference to foo, the module itself, that exists as an object inside sys.modules, but the only name that is bound inside the bar namespace after the execution of this import statement is the name grok. And foo is not bound as a name here. Okay, so that's the second import syntax variation, and behind the scenes it's identical to the standard import. What's different is the names available afterwards. Another variation from module import star that imports all of the exported symbols from the namespace. So in the case of foo, that would then create spam and grok variables at the top level here. It is discouraged, specifically banned by PEP 8 for use in code. It's really useful at the interactive interpreter because you just import everything and you've got immediate access to it. But inside normal code, it creates namespace pollution, where particularly if you do from foo import star and from bar import star, when I'm looking at these, there's nothing in the code that tells me where they came from. I might have name clashes that I'm not aware of. It's much better to be explicit about your imports. Useful for the interactive interpreter, deemed acceptable somewhat inside dunderinit.pys, the namespace packages. Import everything from a submodule name. We'll look at that shortly as well. Okay, so modules as objects. This is a bit more advanced, a bit less commonly used, but quite funky. Dynamic objects. Python has great flexibility in what it lets you customize about object behavior. For example, we can do from unit test.mock import magic mock. We can create a mock object, and then it will create attributes on demand. And when I ask what attributes it has, look, it now has foo and bar now appear as attributes available on that object. The attribute lookup protocol, how an object responds to the dot operator. One of the customization points is the attribute lookup protocol, which contains these methods, dunder_getAttra and dunder_getAttribute, dunder_delAttra, dunder_setAttra, and dunder_dir. So this is for dynamic objects. You don't use this sort of stuff very commonly, but you do it to provide a nicer user experience for the API for your objects. So you make good use of it in limited places to provide a nice, pleasant and clean, self-explanatory API for your objects. So dunder_getAttra, if this is implemented and an object doesn't have an attribute, dunder_getAttra is called. So for normal attribute access, where the attribute exists normally, dunder_getAttra won't be called, but for attributes that don't exist, dunder_getAttra will be called. Dunder_setAttra is called for all attribute setting. Dunder_delAttra is called for attribute deletion, and dunder_dir is when you call dir on an object. You ask for a list of available members or attributes on that object. Dunder_getAttribute is a bit special. That is called for every attribute lookup. Now, and it's implemented on object.dunder_getAttribute. Because attribute lookup is massively common, it is much rarer to override this, and it's dunder_getAttribute is dunder_getAttribute on object that implements the attribute lookup protocol. So if an attribute doesn't exist by the normal method, but there is a dunder_getAttra method, it's dunder_getAttribute that will call that for you. So it's much less common to provide this because overriding every attribute lookup makes you responsible for a bunch of stuff and could well be a very high performance cost. So it's much more common to implement dunder_getAttra. So let's have a look at an example of that. Here I've implemented a proxy object. A much more practical example of this might be for where you have object composition. So you have an object that has another object, and you want to delegate certain operations to the underlying object. So you would intercept some attribute lookups with done-to-get-attra and delegate them to the underlying object. Proxy objects, where you want to protect access to an object. The trouble is that the standard pattern for proxy objects is to do something like have a class, and in the initializer, take the thing that you are proxying, and then you do self._thing equals thing, and everywhere you want to access it, you do a get-attra on self._thing. The trouble is, if you then have access to that proxy object, you can just access _thing, the original object. Kind of maybe defeats the purpose of having a proxy in the first place. I'm not really a fan of trying to prevent people from doing things, so this is just a synthetic example, but we can see these protocols in action. So let's create a file handle as a proxy to, we'll use proxy to create a proxy to a file handle. What have I got? Let's do stock.py. And let's provide access to the read methods and the close methods. So what happens is when the proxy function is called, thing is a local variable inside the closure. Proxy thing, I might have just broken my code. I hope I didn't save that. Here, proxy thing is an inner class defined inside that function, and it has access to thing through the closure, through the local variable. So the done-to-get-attra, done-to-set-attra, done-to-del-attra functions access the object through the closure. We return the proxy thing. Ah, right, I did screw that up. Let's do Python proxy -i proxy.py. So I can now do file handle equals proxy. I did save this, didn't I? Control S. Let's see. No, I didn't save it. Let's try that again. Now I've got it. And you see H is the proxy object. There's no H if we do a dir. If I do a dir on H, that's going to call this method, and it's going to return us a list of the available attributes. I cast it into a set because the most common use case is this in operator. And the in operator in sets, it's a hash table under the hood, is constant. The in operator is a constant time operation, whereas the in operator on a sequence is an order n operation, because you have to check every member. Using a hash table is much faster. So dir returns a list of all the available attributes. It should say just read and close, where of course if we do a dir on a normal file handle, we'd get a ton of those, like seek. If I do h.seek 0, I'm going to get an attribute error from here, because it's not one of the allowed attributes. I can do h.read, which delegates to the underlying file handle, and I can do h.close. And now h.read should fail. So there's a simple proxy object. However, this isn't really hidden. And in fact, Python used to have, back in the days of up to Python 2.1, I think it was finally pulled out in Python 2.2, a restricted execution RExec module that came from Zope, which was a web framework before web frameworks existed. And a lot of Python was contributed by the Zope community. Restricted execution would execute code inside a restricted environment where it didn't have access to things like IO or the file handle module. And it was a Python security expert called Karpin Yi who proved that because of through the behavior of closures, even inside that restricted environment, you could break out. And it wasn't possible to create a restricted execution environment using normal pure Python. We can look for the closure variables on these methods that exist on the class, and you can see that the thing object there is actually accessible as a closure variable. So we don't really hide it. We just make it more inconvenient to access. But there we go. There's a proxy object using a closure. It's the closest thing you can get to true object hiding in pure Python. And that provides attributes, reading, setting, and deleting, and responds to the dir function through the implementation of these protocol methods. Why am I showing you this in a knowledge share about imports? Because modules also follow the same protocol. We can provide dunder dir and dunder getAttr particularly. I think we can provide delAttr and selAttr functions inside the module and customize the dynamic behavior of the module. So one thing we're going to look at when you're creating a package, packages are often an abstraction over a ton of code. And the top level namespace of the package, the dunder init.py, that will typically define and create the namespace for the top level package. It will just have a bunch of imports, a bunch of names that are available for top level imports. Typically, they will have been implemented in sub-imports, in sub-modules. So importing the top level package will automatically import those sub-modules to make them available at the top level. Now, in application startup, module import time dwarfs startup time for anything else in Python. You're going to spend, for a script or for an application, most of your time is going to be spent in import time. And it may be a shame if you've got a package which is an abstraction over complex functionality and a lot of code, you may want to add something like, say, lazy loading, so that submodules are only imported when they're actually accessed. So here's an example module which exposes the names CSV, import, lib, and inspect. They're not really sub-packages. They would be sub-packages in a real example. So if we ask for the dunder dir, what names are available inside this module, it's going to say CSV, import, lib, and inspect. Those don't exist. So when we try to access them on the module object or import them from the module object, dunder getAttr is going to be called. It's going to import the module using dunder import, which is the built-in function that does importing. It's going to set that module as an attribute on the module object. So then the second time it's used, the attribute will exist and dunder getAttr will not be invoked. And then it's going to return the module object. So this is lazy loading. And I have an example of this. Here we go. This is our dynamic module. So I should be able to do import dynamic. Now, if I dir the dynamic module, it could return CSV. But if I look inside the dictionary, let's do .dunder keys. There's a bunch of these, dunder name, dunder doc, underscore attrs exists. My dunder dir and dunder getAttr functions exist, but CSV, import, lib, inspect haven't yet been loaded. So now let's do dynamic.csv, importing CSV for the first time. And now when I look at dynamic.csv, it's just available as an attribute there. And this should work. I didn't actually test this before on dynamic import lib. It works with both forms of the import syntax. So this is dynamic module behavior. Not useful very often, but sometimes useful, and also consistent with the attribute lookup protocol on objects, and it's more common to implement it on objects. So that's kind of funky and fun. Okay, module reloading. Let's see, in dynamic.py, I add I add some new functionality. 42 is obviously the answer to life, the universe, and everything. And of course, I do import dynamic, and now I do dynamic.x. It's not there. The second import reused the existing one, just.modules. Dynamic is dynamic. import sys. Any imported dynamic is going to get the one we've already imported and cached. So, second module, a second mention of reload from import lib, import, reload. That's one solution. Another solution which is possibly easier. Pop the dynamic module out of sys.modules. It's now null, and now when I do import dynamic, now I've reloaded it. The other way, so and we'll see it has to do the lazy loading again. I've just done it, import lib, haven't we? Import lib, reload. If you give it a module object, we'll refresh that module object. It will clear out the namespace, find the source code, and re-execute the latest version of the source code in that module.
Michael.
Yes.
Does that, if you import something and alias it as something else?
That's you've understood the problem with it exactly, Ed.
Okay.
It's like and I will show you the typical problem with this class foo pass. Okay, so let's reload dynamic. Let's pretend this is the first dynamic. Okay, so let's do from dynamic import foo. F1 equals foo, F2 equals foo. Now, of course, F1 done to class. Everything in Python is an object. Every object has a type. You can only perform operations appropriate for the type, and it's the type that's responsible for creating new instances. So every object has a type. Every object has a link back to their type through done to class. And obviously, F1.done to class is the foo type defined in the dynamic module. Now let's do import lib reload dynamic. This empties out the namespace, re-executes the code in the old module object. So dynamic.foo is f1.done_class is no longer true and is instance f1 dynamic.foo now returns false because dynamic, the code was re-executed. We got a new class object. So reload does not rewrite references to the updated definition. It just refreshes module object. It's very similar to this code. So existing instances of the class still have a reference to the old class. Anything that did from module import name will still have the reference to the old definition. Anything that uses super or does type checking or is instance will probably fail. So do not do reloading in production code, but it is a handy trick while you're developing something and need to try it out. Does that make sense? I'm sure it does. Okay, so where are we doing? We're about 2/3 of the way through the time, which is pretty good time, which means the package stuff I probably won't go into too excruciating detail for you, which is probably what you want. Okay, so the next thing, locating modules. So far, I've glossed over when we do import foo, Python finds the source code for the module. So how does Python do that? Well, there's a bunch of places it checks, and they are kept as a list of strings, a real list of real strings. Do we have sys? We do sys.path. So if you remember python-i.proxy.py, I ran some code. If you run code in your normal, normally executing Python environment, the first entry in sys.path is the directory containing the script or the program that's running. So scripts and programs are always able to import from the file system in the same directory as them. So you can distribute applications as a directory of files. It's kind of useful. You can also zip them up. This doesn't exist, but if it did, Python would import the standard library from there. So you can bundle up Python applications with all the parts of the standard library they use into a zip file and import from there. This is my standard Python, the Python that we're using, the standard library, is divided into two for the Python parts and the parts implemented in C. And then also I have my site packages and dist packages for anything I might have installed using pip. The first one being my local for this user and the other two being for the system. So these are all the places where Python checks, and it checks them in order. It's a sequence of strings. If I use the Python, what's going on? If I use the standard Python interactive interpreter, we do import this. One of the two visible differences between the interactive interpreter and a normal running Python environment is that the first entry on sys.path is an empty string, and that just means the current working directory. So from the interactive interpreter, you can navigate around the file system and always import from the current directory, and that's useful. The other change in an interactive interpreter, which isn't available in a normal standard running Python environment, is the existence of the underscore variable, which is in the interactive interpreter keeps a reference to the last evaluated result. In production code, we use underscore to refer to unused variables, and also the get text translation function is common convention is to call it underscore. So underscore is much overloaded in Python. So the places where Python checks is available as a list of strings, sys.path. There are various ways to manipulate this. Environment variables. You can also append locations. It's not that uncommon to do. Maybe you can append or insert at position 0, maybe a directory of plugins and so on. It's much better to install dependencies and other code that you're going to import as packages and use the standard Python packaging machinery and tools for doing that. So sys.path, if you're doing sys.path tomfoolery, it ought to be looked. It's not always wrong, but it ought to be looked at. But it's very useful for understanding Python, understanding where stuff has come from. Okay, so that's modules. So far, we've looked at modules as individual Python source files. Every Python source file is executed as a module or in a module, including the main program. So we have as units of abstraction when we're coding, ways of thinking of ways of dividing our project, our code, our system into components that we can think about. We have functions. We have classes, which group and contain functions and provide objects. Objects have behavior and attributes. And so we have functions, we have classes, and then the next level of abstraction up is the module. We group related things together in a module. So your modules have coherent, sensible names that tells you what lives in there. And when you're looking at this stuff, your application on the file system, you can tell where new stuff goes because it's clear where it belongs. And also looking at a file name, it gives you some module name, it gives you some clue as to what's in there. The module is a unit, a level of abstraction. And the next level from the module is the package, where a package contains many modules or a module hierarchy. And that corresponds directly, typically, to a structure, a directory structure, files in a files on the file system, organized in directories. So a package is the top level directory. And we can, particularly common from languages like Java, to have a lot of namespaces. And we have these and we work with these commonly. So to create a package, you have a directory structure that your code is organized in, where the directory names become the package name and the source file names are the sub-modules within the package. And here's an example package structure laid out on the file system. In order to make this a Python package, it used to be the case that you had to add these dunder init, the namespace files for the package, the dunder init.py. So when you do import package name, it's this dunder init.py that is executed to create the namespace. For package name.utils, it's this dunder init.py. For package name.parsers, it's this one. You don't need those since about Python 3.8 maybe, or maybe even 3.6, some time ago. The dunder init.py is no longer required. You can, if this dunder init.py doesn't exist, you do import package name, you get an empty namespace. It's not required. And you, for the top level namespace, you almost certainly want to define it. But for the sub packages, you may not need there to be a top level namespace. But we're going to look at what the purpose of these dunder init.pys and what should live there coming up. So we have the package, we have the organized code on the file system. We can then import those from those in the normal way. Everything works as it did before, but our import statements can now have multiple levels. There is one distinction, and particularly when you start or you take code that was in modules and turn it into a package, there is a change we need to make. There is a change to the way imports within a package work. Using relative imports. So suppose we're looking to create a package from some existing code, and every package has a genesis. When foo.py and bar.py, if they lived alongside each other, maybe in the same directory as prog.py, foo and bar could import from one another quite easily. If you put them into a package, this directory itself is not directly on sys.path. The directory containing spam must be, so we can contain within spam. So we can import from spam. But an import foo inside bar.py will be looking at the top level. It's not looking inside the same directory. And this is because it's common for packages to have many, many Python source files, and it's virtually impossible to avoid at some point clashing with a standard library module name, which causes a great deal of confusion and breaks things. So normal imports are always treated as absolute from the top level. Modules inside a package can't import from each other using these normal import statements, unless they use the absolute path, which is the spam.foo, from spam import foo. So bar is using the absolute path there to specify the foo module. That works fine. There's also a relative import syntax. These dots. From dot import foo means from the same level in the package as I am, import the foo module. Here, this is from the foo module in the same package as I am, just import name. From .grok, the sub package, import blah, and so on. So this is relative import syntax that only works inside packages. So using the dot syntax, foo, bar, and grok are all able to import from each other. I quite like the absolute syntax. It's really clear and explicit. But I've got used to the relative import syntax, despite how closely it looks like there's grit on your monitor instead of actual code. Okay. So that's the fundamental stuff about creating packages, how packages exist in the file system, on the file system. Packages also define a couple of if you're inside a package, there's also a couple of these extra magic variables created for you. Dunder package, the name of the enclosing package, and dunder path, which is a list of strings, the search path for subcomponents. So the XML is in the standard library, the XML namespace. This is where it lives. But you can actually install things into the XML namespace, subparsers, so it can be found as xml.etree, for example, for the elementary parser, by extending the search path for this package to another directory. So we can extend the XML namespace without having to jam it into that directory in the file system. Which is even better is to let the Python packaging machinery manage this for you. But this is how it's exposed. Stuff like setup tools and the build package, create packages that can do this for you, namespace packages, we call them. So it's not terribly common to work directly with these attributes. Okay, so going back to our creating our packages on the file system, what are we supposed to put in those dunder-init.pys? A lot of people just start coding in there, and I don't like that. Dunder-init.py is not where I go to look for the implementation of a package. I want to have nicely named modules that tell me what's in there so I can look inside the package and relatively easy find what I'm looking for. And the dunder-init.py exists to create a namespace. It's a namespace file. So I like to see as little code in there as possible. The purpose of that file is to define the top level API, to define the namespace, to define the public API for that package. And this allows us to have the dunder-init.py defining the public API for the package, and then the implementation, how the code is organized internally, are effectively private implementation details for the package. Not everything needs to be exposed or be visible at the top level, but everything is accessible in those sub-modules, sub-packages from a direct import if people need to. So we have, for example, a spam package containing foo.py and bar.py submodules. They contain foo classes and bar classes. So as it stands, we can do from spam.foo, import the foo class. From spam.bar, import the bar class. We may want to expose that as a single spam namespace, so that you can do from spam import foo, from spam import bar, and you don't have to need to know or care about the internal organization of the package. We can do this in dunder-init.py by doing from.foo import. We can import foo and import bar inside dunder-init.py, and like function definitions or class definitions, an import statement is an assignment. It creates a global variable. Here it's executed at the top level. It's executed in the global scope, so it creates a global variable. So after dunder-init.py has been imported, triggered by when someone does import spam, this code will start being executed, and then spam.foo and spam.bar will give you direct access to those classes, and the user of the spam package doesn't necessarily need to know about the internal organization of the code within the package. So dunder-init.py here defines the top level public API. Only names that we're exporting at the top level are imported in here. And there may be utility stuff, which is accessed less frequently, where there may be use cases for people doing from spam.utils import. Not everything needs to be accessible at the top level. If you want a case study on that, have a look at the async.io module, where the dunder-init.py is actually a package. You use it as if it was a module, and all of the implementation lives in submodules. And it uses import star, which I'm not wild about, but there you go. Modules, packages are free to define dunder all as a list of strings that defines the public API, and that defines what from module import star. Only names exported in dunder all will be imported when you do a from module import star. We don't care about from module import star because people shouldn't be doing it anyway, but it is nice to explicitly define the public API of a module at the top of the module like this. It's nice documentation, and there are tools that do take notice of it. So I have inside the example code, we don't have time to look at it in detail. You'll be pleased to see there's a module stock.py, which is an example code which defines a stock class and some functions for reading the stock stocks from the stock CSV file, for printing those out. There's some various different formatters that we can use for that. The exercise, which I won't take you through, is to turn that into a package. And there's an example of the results. We can see in the dunder init.py, all we do is we import the top level names from the submodules. We have a stock submodule, a reader submodule, and a formatter submodule. All of the implementation is divided across these three submodules, each of which are smaller, shorter, easier to maintain, easier to write individual tests for. The top level dunder init.py exposes exactly the same API. It imports all the names that were available here. So users of the stock.py module can switch to this package. We can switch the implementation to a package, and it presents the same API. It's backwards compatible. So there's no cost in the change to the user. And the main difference in the code was the CSV reading functionality needs to use the stock module. So it now needs to import it. So we need to reorganize the code slightly. This could also be from .stock, import the stock class. And that's really all there is for making that work. So it's possible to start code as a module in a single file, and as it grows, change it to a package in a backwards compatible way.
Michael, can I just ask another quick question about that? So
Yep.
I really like that pattern. That's what I would like to do as well. But it's a convention, right? You can't actually. People could still import
Yes.
from the submodules.
Yeah, it doesn't prevent access to any of the subcode. It is, you do see in some, so underscore CSV. So CSV is the top level pure Python module. The heavy loading is done inside underscore CSV. So you sometimes see module names. This might be underscore reader underscore stock, which follows the Python convention of adding the leading underscore to signify that it's private, while still not preventing you from accessing the contents via the usual imports. I prefer to determine the public API by documentation and stuff that's exported here, using stuff like dunder all, because I think having underscores in names inside a package is kind of yucky. So convention over enforcement, you know. But you are correct in your understanding on what you say.
Cool. Yeah, I remember that happens a lot in PyTest. A lot of the types in PyTest were defined in sort of private modules that were deeply nested in the code. But if you wanted to go full on type checking, you needed them. And so I found myself importing various PyTest types from deep within bits they weren't really wanting you to look at.
The extra overhead of all the type checking.
Once you've started a collection. Cool.
Okay, so
thanks very much.
These few slides, we have a couple more slides to go and then we're done. These few slides illustrate the work of changing a module into a package, including changing the imports. And what you'll find, note that what we found is that the reader code, for reading stocks, imports the stock class, because it's creating a list of stocks using this class method here. So we've got a dependency here. This exercise of splitting the code up reveals the dependencies within the code. This code is dependent on that code. And this is where you might find you've created this tightly coupled interdependent mess that is really hard to break up into modules and reveals that you need to do something about your coupling and dependencies. And this is how you can end up with code that has circular imports. So here we've got span child.py, we've got the span package. It has child.py, which defines a child class and imports the base class to depend on. the code inside the base class has a function somewhere. There's some convenience functionality implemented in child.py, which is used inside a function inside the base module. So we import, there's some code executes, it starts executing, and this is where the order of execution matters and how things are created. At some point, we started importing from spam.child, which creates the empty module in sys.modules and starts the code execution here. It gets to this line of code, which imports from here. So there's a new empty module in sys.modules. We start executing the code from .import child. Circular imports are allowed. So this child namespace, I've done the executions the wrong way around. But anyway, if this was from .child import thing, .child inside sys.modules is empty. We get an empty module there. If we attempted, suppose there was something here that inside class here that attempted to access child's function or something, it would say that doesn't yet exist, attribute error. It doesn't exist at this point, child is just an empty module. It's only when base.py has been, when the execution is completed, then the base namespace is available. I think the problem comes if we execute the code this way around. If we import spam.base, it creates the empty module here. It immediately starts, because all imports always live at the top, don't they? Immediately starts import child. Child wants to import base, and the base module exists, but the base name does not yet exist. So this import will fail. We've got a circular import. So how do we solve that? What do we do if we find ourselves in this situation? There are a few fixes depending on exactly what's going on. It's likely that this child module is used inside a function somewhere. We don't actually need the name until runtime, so we can move the import to the bottom. So this code starts executing, it imports from .base, which executes all of this code before it gets to here. And by the time it gets here, the base name already exists. It doesn't fail. Another way, move the import. If this import is only needed inside a function, move the import, have an inner import into the function. An inner import inside the function. That's a common way of fixing it. And if you have two modules that have a circular import like this, what it typically tells you is there is one chunk of code which is a child dependency of both. So move that dependency into a third module, and now you've got no circular import. So those are three different ways of fixing it. Move the import to the bottom, move the imports to be an inner import inside a function or method, or factor out the shared code into a third module. Those are how we solve circular imports. And just as you can do Python-M module, you can do Python-M package by defining a domain.py. And one common example of this, if you do Python-M unit test, it launches test discovery. There are no tests. If we do Python import import unit test, unit test under file, that's actually the dunder init.py. Unit test is defined as a package, and we can do open. Let's do import OS, open os.path. Join pathlib is much better for this, but all of this, os.path.split unit test.dunder file. You want to take the base path, which is the first component that comes out of split, and join. If we look at dunder main.py in the same directory, you'll see that exists, and it's dunder main.py that actually launches test.discovery. So dunder main.py is what's executed when we do Python-M unit test. And you can do that for sub-packages as well. So a package can provide a bunch of executable tools. And that is the end of the material I have for you. Thank you for listening and being good sports. Any questions? Do you still have your hand up, Ed?
No, I don't.
Okay.
Thanks very much. That was great.
All right. Thanks, everyone. Until the next time. The next one will probably be in a couple of weeks. And I was thinking of doing maybe some more advanced Python topics. We looked at the attribute, dynamic attribute access. There are descriptors, which are pretty cool. Metaclasses are worth a mention. The dynamic dunder init subclass for specialization through inheritance. It's like class decorator is a way of avoiding using metaclasses. For a framework can customize its own subclasses. I'll show you a practical use case for that with the GigaClear UE test package that Eugene created before leaving. So that should be fun.
Cool.
See you guys.
Thanks.
Thanks.
See you later.
Thanks a lot.
Cheers.
Thank you. Bye.